And hello, welcome everyone back to our turbulence modeling background. We are talking about the background behind the kOmegaSST model. And in the last video, we were talking about the 1994 version of the kOmegaSST model, and we talked about how this production limiter actually helps us when it comes to adverse pressure gradients and flow separations. So this production limiter limits the presence of turbulence viscosity in such regions, and it helps to make it match experimental data closer, because the tendency of this kOmegaSST model is to over-predict turbulent viscosity in such regions. Now, this is the 1994 version of the kOmegaSST model. So the story is this, that people have used this model for like 10-ish years, and basically they found another problem with it, and this one is by Menter again. It's in this paper called 10 Years of Industrial Experience with the the SST turbulence model, which is the kOmegaSST turbulence model. So this is what they describe here. Okay, so what they describe here is in a second problem called stagnation regions. So stagnation is okay. Where is this stagnation region? So this is our last what do you call that, video stuff. I can just clear this up. So let's see, stagnation. So I have a brush here and now I'll draw a sphere. All right. So imagine a sphere in some free stream. So there is like some fluid blowing onto a sphere, and eventually as the fluid gets closer and closer to the sphere, the velocity in this direction, let's say this is ux, so this is x direction. At some point the ux point, okay, ux equals to 0. All right, ux equals to 0 at this point. All right, so ux equals to 0 is at this point, and this point is known as the stagnation point. Okay, stagnation. Stagnation point. Okay, you do a quick Google search online and that's what they will show you. This is more or less the correct way of describing it. And what's the problem? The problem is that in stagnation region, large normal strain produces excessive turbulent kinetic energy. So what is it saying here? Alright, so here is the stagnation region, right? What it's saying is that large normal strain. And what's the large normal strain? Usually normal strain is, we commonly know it as du dy, and remember we have this velocity profile. Okay, large normal strain is just this velocity gradient. We call it a strain rate of sorts. Okay, so this is the large normal strain, and this velocity gradient tends to produce turbulence. Okay, produce turbulence. Okay, so this is normally how that happens. How the production of turbulence happens is usually, it's usually through this mechanism, and that usually increases the turbulent kinetic energy. It increases the nu of T, turbulent viscosity. So yeah, one of the illustrations found helpful was in Fluid Mechanics 101, Dr. Aiden. So he explains a little bit of this in his Spalart Allmaras video. Okay, and if you go on YouTube, you'll find it here, and this is his video. I highly recommend you watch it, and some of his other videos as well. Basically, what he says is he likes to think of it like so. When you have a very large mean gradient velocity over some small distance, so here, because the relative velocity is high, there's so much energy, and that tends to produce this energy. You know, it's has to go somewhere, and it goes into producing these eddies. I'm not sure if I've paraphrased it correctly, but okay, the idea is that when you have large velocity gradient or large strain, I mean, the fluid can okay, let me think of it. Okay, so I will think of it like that, right? Okay, this is a very small length scale, and then we can take the difference in velocity to be delta U, and when you have this small length scale, right, and then you have a large delta U, well, you can think of it like that. Okay, so this delta U is basically, you know, the difference in velocity between the point here and here, and we know that the velocity gradient is del U del X or del U del Y. Okay, so this is delta Y. Okay, so the delta U, the characteristic velocity in this region, equals to let's put it here, delta U. All right, so if we were to have some Reynolds number, right, we will have a characteristic velocity times the characteristic length scale over the kinematic viscosity. So this U, this characteristic velocity of the system, is delta U, and this L is this length scale, I would say, delta Y over nu, and this delta U is just du dy delta Y, and then delta Y comes out again, delta Y over nu. So we have del U del Y into delta Y squared over nu. Alright, and so this means that when you have this rate of strain into some delta Y squared, okay, this is my own interpretation of it, when you increase this velocity gradient, this will increase in the Reynolds number. Okay, so that's how I think of it. It's a dimensional argument. So that's what I think of this this way of thinking of, increasing this velocity gradient will increase turbulence, all right, because it increases the Reynolds number. So that's how I think of it. The higher the velocity gradient, the higher this local Reynolds number, so to speak. Okay, so this is one way I like to think about it. It makes like mathematical sense to me. So okay, yeah. So otherwise, you can go with Dr. Aiden's way. I think he's very good as well. I take a lot of inspiration from him. So yeah. Anyway, so yes. However, you would find that let's see. You would find that this actually over predicts. Okay, over predicts nu t, or over predicts the nu t or turbulent kinetic energy here. All right, so it over predicts turbulence in this region, the kOmegaSST model. At least the kOmegaSST formulation of this kind of over predicts this. So what it means is that okay, the production of K is too high. All right, that's what they found from experiments. So okay, we talked about stagnation regions, and we said that the production of K is too high, and Okay, large normal strain produces excessive kinetic energy. Alright, so I'll just type this in here. Okay, normal strain, so equals to U partial Y. Okay, and then if we were to have this kind of a setup, okay, I will get down and yep, where is it? Oh, my pins, yes. Okay, so yeah, I will have this setup where you have delta Y, and then you have A, likewise delta U. Okay, delta Y, okay, okay, this is a delta U. Alright, let's do this here. Okay, so I just want to record this down. This is pretty important for me. Alright, okay, characteristic length scale equals to delta Y, characteristic velocity scale equals to delta U, Reynolds number equals to U into L or UX over nu. So delta U delta Y over nu equals to partial U partial X or partial U partial Y is the strain rate. Okay, delta Y. So that's how we get that formulation. Squared over nu. So increasing strain rate increases Reynolds number, right? Okay, anyway, that was just repetition of just now. Anyway, yes, in stagnation regions, yeah. So remember the sphere example? Yeah, so we have this problem of the kOmegaSST over predicting the turbulence here in this scale. Okay, I'll just put this down here. Alright. Okay, so to compensate for this, a limiter is used on the production rate of turbulence kinetic energy, which is why you see this here. So the tau ij del u del x, this is the strain rate I was talking about, and this is actually, if you recognize this, beta star omega star k equals to, if you remember, is the epsilon. So the production of k, it's capped, because this is a minimum. You cap it. We cap production of k at epsilon, or 10 epsilon, which is 10 times dissipation rate. Okay, so that's basically where we get this term from. Okay, we get this term from that. Alright, so yeah. So here are more references, and this is his paper, the 10 years turbulence model, and this is known as the 2003 update, and as of 2020 OpenFOAM uses this model for kOmegaSST in their code. So this is kOmegaSST for you, the very long and short of it, the summarized version. So the key features of kOmegaSST, a lot of it comprises of data fitting and empirical testing, and it uses the kOmega in the boundary layer region, k epsilon in the bulk region, and despite this, we still have problems with the adverse pressure gradient. So there's a shear stress production limiter in the gradient boundary layer region. So to deal with that, this was the way we redefine the kinematic eddy viscosity. That's why you see that there. And also, to deal with this stagnation problem, we limit the pk over here. That's why your pk is defined as such. The rest of it is pretty standard, and it will, it's the standard blending functions that switch it from k omega in the boundary layer to k epsilon in the bulk region. So that's the theoretical background behind kOmegaSST, and thanks for watching. I hope to see you guys next time. Goodbye for now. Yeah.